Welcome back, highly hyperbolic coding chamber participants. Don't forget to join the Discord. It's absolutely jumping. There's 100, maybe 200 people in there. Also, I think this is day 16 or day 17. Still going to be doing, I don't think I'm going to do any of, maybe we'll do maintenance, or maybe we'll do add two numbers. It's probably more important that we do add two numbers. Actually, I'm probably just going to do maintenance. I'm a little burned out. I'm post an assessment that I'm just gonna say I fried. You could say I wrote the assessment actually, but I wanted to shout out Android Hacker. I think his name is Android Hacker. But this man said, "Thanks, sir. I'm also continuing my journey with you." Well, thank you for joining us, brother. You will be blessed with many riches and many great, long life, healthy family for subscribing. So appreciate that. I also think it's cool that more people think it's cool to do LeetCode. So that's pretty epic. Yesterday I got fried by symmetric tree, even though I wrote like I said the title was symmetric tree, more like symmetric free. But I actually got fried by that problem. So yeah, the assessment was like 2 hours long, so I'm a little fried, but the grind does not stop. Should be grateful for the grind. And there's 20 minutes, so I should do this problem again, but I think I'm just gonna do maintenance, and then maybe tomorrow do a longer session where I'll do just a old problem, new problem, old problem. But like we said with the leaky bucket thing, it's probably if you have a bucket and the bucket is your knowledge base, or the bucket is your brain and the water is the knowledge base, it's probably more important that the bucket doesn't leak water than the bucket, and you can put more water in the bucket. Basically saying, if your bucket's leaking water, there's no point in adding more water, right? It's kind of like a futile thing. So this is the justification for maintenance today. We'll do 20 minutes, see how many problems we get through. I don't think there's going to be a lot of teaching or a lot of explaining, not a lot of Feynman methoding. So I might just try and solve as many as I can. Dopamine ticker in my brain is going fast, so I'm going to do 20 minutes starting now. So you have random weighted, move zeros. Very familiar with this problem. This is a two-pointer method or sliding window approach. We have move zeros, which is an array of numbers, and we're not returning anything. We have to modify nums in place instead. So given an integer array nums, move all zeros to the end of it while maintaining the relative order of the non-zero elements. Note that you must do this in place without making a copy of the array. So basically we have to move all the zeros in this array to the end of the array. And we have nums 0, 1, 0, 3, and 12. And the output is 1, 3, 12, 0, 0. So there's one way that we can do this where we iterate over. Could you minimize the total number of operations done? So we'll try that follow-up. If we do have 0, 1, 0, 3, and 12, well, we could use a sliding window approach where we keep track of our zero index, our current zero index. Whenever we run into a number that is non-zero, we'll swap with our zero index and increment our zero index. This way we can keep shuffling all the threes, all the non-zeros into the end of the array. So that would look like, okay, we have 0, 1. 1 is not 0, so we'll swap 0 with 1. And then we'll have 0, 1. We'll have 1, 0, 0. Keep iterating. 3 is not the same as 0, so we'd swap 0 and 3. Then we get to 12, and we increment that. So it looks like we can just keep LZI, which would be last zero index, of I equals 0, I is less than nums.length, right? I plus plus, and then we're going to say if num sub I does not equal 0, right? Then we want to swap these values. So we're going to say const temp equals nums sub I, and since we're holding num sub I, we want to replace it with num sub LZ I. And since we're replacing num sub I, we want to replace nums sub LZI with temp. And then at the end, we'll increment LZI so that we can continue to swap those zeros as we move towards the end. So if that looks good, we're looking at linear time with constant space complexity. So if that looks cool, pass, and then we'll go to the next one. We'll go for binary tree Inorder Traversal. This is the one where the recursive solution is trivial. Could you do it iteratively? So we have a root of a binary tree node, and we have to return a number, an array of numbers. So given the root of a binary tree, return the Inorder Traversal of its nodes. So an Inorder Traversal is just a method of depth first search where the order that you visit the nodes in order means that L, the center node, would be the middle node that you visit, so it'd be L and R. Easiest way to do this is with recursion. So since we need to return an array of numbers, what we could do is we could call this helper function, right? We'll pass in the root node, right? We'll pass in our array, right? And we're going to use this array by reference, modify it, and then return it. From here, we can just implement this Inorder Traversal with the recursion. And we're not going to return anything. And so how do you get started, right? So we just have to do L and R. So what that means is if the node exists, right, then we want to operate on it, right? And if that's the case, right, then the first thing that we want to do is do L and R, right? So if that's the case, the next thing that we would do is we would call helper, right, with node.left, right, passing in nums, and we're actually missing a parameter here. Nums, which should be an array of numbers, right? And then from here, right, what we'd want to do is we could do node.val equals, wait, I'm getting confused actually. Oh, right. Instead of doing node.val, we do nums.push node.val, right? And then we would call helper node.write with nums. And so this is just be a basic Inorder Traversal of the node's values. That looks good. The time complexity of this is going to be linear time, I believe, because in the worst case, the tree is just singular. It almost looks like a linked list, but reversed. So it would just be, you know, maybe just one node with node.write, in which case you would just visit every node. But in general, it kind of doesn't matter because you have to visit every node anyway with depth first search. So it seems like it would be linear time, and the space complexity would be bounded by the space complexity would also be linear time, I believe. I mean linear space. Space complexity, yeah, would be linear space. So the follow-up is, could you do it iteratively? So could we do an L and R iteratively? I think you could. I'm remembering another solution where someone did it with a queue. So maybe we'll try that one. Maybe that one makes more sense. So I'll move this down low and we'll try it with a queue, which is just an array, but we're going to operate it like it's a first in, first out structure, which means if we push to the end, we'll take things out the front. So if that's the case, to start, we would say while, and we'll just use cur, which we're gonna bind to root, and then the goal here would be to do a in-order traversal on this binary tree, right? And so we can return this array of numbers. So we'll still need that array of numbers, and so we'll say while cur does not equal null, right, and q dot length does not equals, or not and, but or, right, then we want to get to work. So what we would do here, right, is we would do, so now we'd be at 1, right, but we don't want to process 1 yet, we want to process left first. So if we want to process left first, we could say cur dot, we could add cur dot left we could add cur dot left to the queue. No, we probably want to do left first. We probably want to go into cur equals cur dot left, but before we do that, what would we want to do? We would want to push onto the queue cur and cur dot right. That way we'd be free to process or go as far right as we want. Additionally, we could do it like this: while cur does not equal null, we'd push these forward, and so what would happen here would actually be that cur dot right, so we're pushing both of those onto the stack, onto the queue, and then cur equals cur dot left, so we're going to go as far left as we can until it equals null. When it equals null, then we actually want cur to equal q dot shift, which should take one from the front. And once we take one from the front, once we take one from the top, that would mean, so if we go to root, we'd go left, we'd push 1 and 2 onto the queue, and then we'd go cur left, that would be null. So then we'd do q dot shift, so we'd be at 1. What do we want to do at 1? We do the processing step here, so we do nums dot push cur dot val, right? Cur dot val. So we'd have 1 in the array, and we want to go to 2 next. The way we would do that would be just doing cur equals q dot shift again, and then going to the top. Cur wouldn't be null and q wouldn't be empty. Actually, q would be empty because 2 wouldn't be in it anymore. But while we're at 2 now, we would push on to the stack 2 and actually we don't need 2 q dot shifts because it's going to just come back around. So we do cur equals q dot shift, we'd be at 2, or it'd be at, so we're okay, we cur dot left, right, we do q dot shift, now we're at 1, we push 1 onto the array, go back up, cur isn't null, cur is null but the q isn't empty, and cur is still null. Actually, cur wouldn't be null because cur would equal 1. but I don't think it matters because we go back to the top and we do cur equals q dot shift, so we'd be at 2 now. Actually, so you actually do, I think you actually do want to do cur equals q dot shift. That would put you back at 2, from which you would go, you'd push 2 back onto the q, and then you'd push right as well, we go cur equals cur dot left. Yeah, this method, I'm using the stack paradigm, but with a queue, so it's confusing. I think we need to do this queue-like. The reason we use a stack is because when we add things onto the stack, we can pop them off to get where we were at, and that's kind of how we're using the queue, which is why it isn't working. I think with the queue, you don't need a while loop. You can process things in the order you put them in. So if you start at 1, you can push. You start at 1, you can push cur dot left, cur, oh, so maybe this, maybe the queue that I was using in the other problem was a breadth first search. We'd start at 1. If we push cur onto the list, then we'd have 1 and right, and then we could do cur equals cur dot left, which would be null. If cur equals cur dot, if cur is null, then we shift and we go back to 1. So I think this should just be a stack, and we'll just change all of these. So I'll make this a stack. And so when we do this, we can do stack dot push cur, right? So we'll push 1 onto the stack, and then we'll go left, it'll be null, right? And since we're null, what we can do is just do stack dot pop to get exactly where we last were, right? Because it's last in, first out. So the last thing we added, which would be 1, we would pop that, we get 1 again. So we can push 1 onto it, right? And then from here, our goal to go right would just be to do cur equals cur dot right. So now it'd be at 2. 2 wouldn't be null, so we'd short circuit. 2 is still not null, so we'd push 2 onto the stack, and then cur, you'd go cur equals cur dot left, right? And then we'd be at 3. Well, 3 wouldn't be null, so we'd do cur, push 3 onto the stack, and then we'd get to null. We'd pop that. We'd be at 3. We'd push 3 onto the stack, and then we'd go right, but it'd be null. And since it's null, we do cur dot stack, cur equals stack dot pop, which would be 2, and then from there we would be Gould. So I don't think it's necessarily the code blocks itself, but it's literally the code itself. If you wanted to do post order, I think you would literally swap this. So this would be LRN. So go as far left as you can, then go as far right as you can, then go as far left as you can. We'd get 3, then 2, so far left, then as far right as you can, then far left, then N, then as far, and then 2, and then 1. So if we run this code as is, it should give us just realized the display. Stack.push. This should give it to us. This should give it to us in reverse. So we'd be at 1, we push 1 onto the stack, then we do cur.left. There's nothing to do, so we go right. That wouldn't mean anything. So we actually couldn't go right there. Maybe try to go. Yeah, I need a better way of doing this. I think this cur.stack.shift thumbs up push. So we got the stack. Once we come out here, we want to do stack.pop. We push the value onto the stack, then do equals cur dot right. And I think this should be fine. Oh, we're returning Inorder Traversal. This node says return nums. Oops. That looks good. We definitely need so yes, that is a wrap. That looks good. Time complexity, this would be linear time. Linear, oh, they're saying, well, this is, I think, the recursive approach. This case, space car is log n, average case is, log n, where n is the number of nodes. So yeah, linear space as well. And so that looks good. I just realized halfway through that my screen default recording was messed up. So apologies for that. It will be fixed tomorrow.